Hello everyone, we're back with another episode of Computer Vision Talks, and today we have with us Ameya. And Ameya works on continual learning, which is a common interest between me and Nikhil. We are excited to host Ameya today because we are going to learn a lot about practical continual learning. And off to you. You can start.
Yeah. Hello, everyone. I'm Ameya Prabhu, and I'll be presenting the things I learned recently about continual learning. So let's proceed. Let's dive in. Firstly, as a brief outline to the talk, uh, first I'll discuss like what is continual versus static classification. I'll align what we do in research with what happens in practice, like what do I think will be usable continual learning. I'll go to some assumptions because mainly the gap is in assumptions, in my view. Then I'll just show some interesting directions I've seen, and this is going to be the outline. Let's get it. Let's get into it. Firstly, what is continual learning? I'll just give a brief overview. People usually train on static datasets. They just get a dataset. They like can do hundreds of optimization passes in this, and they get a model. Continual learning leads with the issue when new data arrives, because now we need to like learn on the new data but not forget the old data. It's like an optimization on a complete data set again. Doing this again is kind of expensive and we need to minimize the cost. And this can be viewed as essentially learning from a fire hose. There is a lot of information being thrown at you, and you have to learn as much as you can, as fast as you can. You can't do the typical like hundreds of optimization passes. That's how I understand continual learning. It's simply this. This is like you have a lot of information overload, and you have to learn from whatever information you're getting. It's very fast, and like you have to see how much can you learn, how fast can you learn. This is essentially the problem of continual learning, in my view. So let's first see what really is the gap between research and practice, how to get usable continual learning. The first claim I make is that continual learning is not essential. When you have new data arriving, you could just fine tune your models. That is a real possibility we need to consider. What makes continual learning useful? When is it? First, the training time has to be much shorter than conventional training. Secondly, the performance should not be lower. If the training time is shorter and the performance is the same, then will continual learning be useful in the industry? Is this the case? Well, from Professor Kanan's slides, like they had a recently nice work in a CL Vision workshop where they show that like recent methods use more compute than training from scratch. This is not really viable, and hence people in industry think that continual learning is a nice idea, but it's irrelevant where it is today. And what I think is that we need to change this. What about, can we fix this? Can we fix continual learning algorithms? We find out in our CVPR work that it's not like the continual learning algorithms are just not suited for limited compute. Reducing the compute impacts the algorithms quite a lot because most of the performance that they gain are by just doing more computation. If we normalize computation, then what we find is the best way to use compute is just tune on like past data with like simple SJD, nothing fancy. This is what the industry sort of does when they get new data. They just take the new data, concatenate it, like make bigger data sets, and just tune a model on this. Simple. Now, what to do about this? To make continual learning useful, we need to evaluate continual learning algorithms under certain assumptions. And those assumptions is where the nitty-gritty comes in. This is why continual learning algorithms currently are not as great, and I think they can be made much better. Let's start with the line and assumptions. Why is no one using continual learning? Well, my claim is that there are a lot of assumptions on which you can do continual learning. And if you propose works which work with one set of assumptions, it might be hard to translate them to another set of assumptions. And like there might be discrepancies here. We need to choose our assumptions wisely and align these assumptions with whatever the needs are in, say, like real companies where they have these data, this information fire hose, and they want to learn from this as quick as possible. Okay. Some assumptions are useful. It's important to make assumptions to simplify hard computational problems. That's why we make assumptions all the time, so as to give a clear problem which is much more which is simple and tackleable. However, if those assumptions do not reflect the real world, then no one will use the solution proposed. One approach I will talk about throughout this talk is continual learning with memory constraints. They impact the continual learning algorithm a lot, and storage is very cheap. Hard drives are virtually free. If pe- people design algorithms using this constraint, it's likely that a lot of people won't use these algorithms. Okay. What assumptions reflect real world? We tried to detail this in like my old work, GDOM, on like on like how does literature simplify the constraints? Why are some constraints really bad? But I'll again give a brief overview in this talk with a slightly shifted perspective of what I've learned over these years from 2019. So let's start with categorizing the assumptions into the good, the bad, and the really bad. Let's start with some good assumptions. Well, it's good to classify continual learning into offline and online continual learning, is what I believe. Why? Because online continual learning requires rapid adaptation. We can just ask the question, does this application that I'm training for, does the data require me to rapidly predict on the new arriving data? Or is it just that I get a batch of data and I have to incorporate this into the current knowledge I have with the current data? If I require to rapidly predict on incoming data, then it's online. Examples of this is something like your Twitter or your Instagram. You have new posts being uploaded to your social media network, and you need to tag them with like, is this biased information? Is this something incorrect? Is this misinformation? Is this deep fakes? This needs to happen pretty fast because this information should not be propagating throughout your network. In those cases, you need algorithms which can adapt to rapidly changing deep fakes and this kind of data. This is when you need online continual learning. In cases where you just have like monthly new data which comes to your company, and like you need to update your model, you need to update to latest fashion trends, you need to update to whatever latest bird discoveries have been happening, you need to adapt to seasons, you need to have your self-driving car adapt to the weather scenarios which are expected in the coming months, then you need offline continual learning. This is the essence of the discrepancy. And the result is that for online continual learning, we must measure, is the algorithm able to rapidly adapt? This is a critical thing there. We'll come to that later, but this is the difference between online and offline continual learning. Okay, let's start with compute budget. What will be a compute budgeted offline setup look like? You get some data, you append data to the whole data set, and then you need to train your model with some limited budget. Because if you have very large budgets, it's kind of similar to fine-tuning the model. We need continual learning algorithms to perform well, which is gain equal performance to offline train, to simply fine-tuning the model with very few updates. If we achieve this, then we can deploy continual learning algorithms in the real world. Otherwise, people will just concatenate data and train a new model. And secondly, we need to have no memory limitation. I will come to this later again, but this is very important. Storage is very cheap. We can just store everything. So store everything and learn with limited compute is the setting that I think we need to solve. And once we develop good algorithms for this, people in industry should start using continual learning algorithms for whenever they have new data coming. Okay, what does a compute budgeted online setup look like? It's something like this. You have a stream of data, you have like samples coming, you have like a single sample coming or like a batch of samples coming. You need to predict on the samples. Then you get some sort of labels like that, oh, this was actually a deep fake. some curators tell you that like, oh, you made a mistake here, and then like, your algorithm needs to rapidly adapt to this change. This is the key online setup that needs to happen, which is you get new data, you predict on it, you make some mistakes, someone tells you that like, hey, this is a mistake, and your algorithm should update very rapidly. And this is within the compute budget. You can't take too long to update, otherwise the stream is long past. All right, this is the online continual learning algorithm for compute budgeted applications. So what are the key changes that we make in our works? The key changes that we make in our works is that we equalize compute. Note that online continual learning algorithms have paid attention to the compute budget, but they simply measure compute budget, but don't equalize it. And when you equalize it, interesting things happen. Second important thing to notice is that we don't have any memory limitations again. I will elaborate on this point later, but this is important. You can store whatever you want, but what you need to do is rapidly adapt to new data. Okay. Now, those are the good things: online versus offline and compute budgeted continual learning. Now, what are the bad things? Things that I see happen in continual learning and I really want to avoid in my future work. First is tasks as constraints rather than test cases. What do I mean by this? I got this inspiration from a talk by Professor Kannan, where the assumption that class incremental learning is a task I want to solve, like this is a thing, this is a setting I want to solve, is really bad. And we should not be doing this. Task incremental learning or like class incremental learning is not a setting similar to semantic segmentation is a setting or object detection is a setting. It's just one edge case of a streaming classification task. You have information coming, you have the information overload, data can be coming in any order, and class incremental learning is one specific edge case of how the data can be arriving. When people make it a constraint, we'll see how things go bad. Let's take a simple example. Let's take continual Sephardim. And to illustrate where things go wrong, let's take this class of algorithms that I call two-tier continual learning algorithms. There are many such examples. They're very popular in methods which grow the architecture. They're very popular in like continual meta-learning methods. They're very popular in prompt tuning methods, which are recently very popular. What they do is something like this. They will first predict which task ID it is, and then predict what class it is within this task. Okay, how does it look like in class incremental settings? Say I have a continuous CFR, 10 classes. It's a 5-class. You have 5 tasks arriving over time, and 2 classes per task. So the hierarchy is very clean. Your first layer, the meta predictor or the meta algorithm classifies which task does this belong to. And then you have a smaller learner which classifies, oh, in this task, which class is it? Similarly, if you gate neural networks, then the gating mechanism predicts which network to use, which will depend on the task. And once you decide the network, then the network says, oh, which class is this among the samples in the task. This works pretty well for class incremental learning. That's why it's just bad. It's not ugly. But what happens if I have continual IID classification? The idea here is something like you have just more data over time. And with more data, you probably have more samples per class, and you can perform much better if you continually update your network. Here, they have a lot of issues. Any two-tier continual learning algorithm, the task classifier, the classifier which predicts which task this belongs to, provably achieves random performance because all the tasks are the same data. It's just more data incoming for the same classes. You can't predict which task it's coming from. Furthermore, once you have predicted, like you just select a task at random. For that specific task, you still have to do the full 10 class classification. Your much smaller network is now given the load of the complete 10 class classification every step. And typically they have the assumption of orthogonal tasks. That's why they can create this nice hierarchy. This leads to no performance improvement with increasing data. And this is also really bad. Like the key goal in this continual IID setup was that with more samples per class, you will get higher performance. This is why I claim this is a bad assumption to have any distributional properties of data stream. We should only assume that like it's an information overload coming at us. We have to learn fast from this information firehose. Okay. How do we materialize the solutions? First, we should explicitly make no assumptions on the stream distribution. If you look at GDOM or you look at our CVPR paper, we explicitly say that we don't constrain the incoming distribution. And this is important. Secondly, simply assuming distribution invariance doesn't really help. What we need to do is evaluate on different kinds of streams and see that our continual learning method performs well on all kinds of streams. What are different kinds of streams? First is the class incremental stream, which is just in the information firehose, you have new samples of samples of new classes arriving over time. Data incremental stream is just the continual IID stream that I discussed before, which is you have samples of the same class incoming over time, except your number of samples per class grows over time. And third is the time incremental setup that we describe, where what we do is instead of testing different edge cases for ordering, we just take data sorted by timestamps. This essentially gives us how did data come naturally in natural sequences. How was the information firehose like for companies like Flickr who need to classify samples incoming on their servers. So this mimics a real world stream. So with these three streams, we cover a real world case, which is the time incremental stream, and two edge cases, which is like, oh, what if you just have IID samples incoming? Or what if you have new classes incoming? We should test on all these kind of streams, and your continual learning method should be robust across these streams. Next. Now we go to the next bad thing that people do. They test on small scale datasets. Why is this not useful? On small scale datasets, you can just retrain your models from scratch, and it's not that expensive. Ceph 10, you can train a model to like 94% in less than a minute. Similar for Ceph 100. You don't require a lot of time to train this. What we need is large datasets to ensure that the continual learning algorithms work at scale. To be clear, I'm not saying that large scale datasets are essential. Torr datasets can function as an effective benchmark for simulating these large datasets. But when you use large datasets, when I was running experiments on YFCC 100 million, I could see how compute constrained I was. There is no way I can continually train my models for that long. Otherwise, I'll require like a month to finish a single experiment. That makes the constraints apparent that I could store YFCC very easily. It's 2 terabytes. I have 100 terabytes on my server, and typically servers have very large storage capacities. But we lack GPUs. GPUs are expensive, and the sequential training takes long. And these large datasets essentially make these constraints more apparent and clear for what should we make an assumption on and what should not we make assumption on. But they're not essential. We can train on toy datasets, but we need to ensure that it scales to large datasets. Okay. Now, let's go to the ugly parts of assumptions that people make. And these assumptions are really bad. Firstly, let's go to memory constraints. A large fraction of continual learning works in literature constrain the memory size of past data. But there is no valid justification for this tiny memory. We shall explore this in detail. Why do they justify this memory limitation? They primarily give two reasons. They either say, well, storage is expensive, we need to limit cost. Or they say, well, we can't store past samples because sometimes we need to delete past samples because of privacy constraints. And we want to respect privacy constraints, hence we have limited access to past samples. Let's look at these two constraints people impose. How correct are they? How reflective of the real world are they? Let's say. First, cost. The cost constraint has always puzzled me because storage is not cheap. When I say memory, I don't mean RAM because we don't need to store datasets in RAM. we need to store datasets on hard disks. And hard disk storage is extremely cheap. My mobile here has 1 terabyte of storage. It's really cheap. However, what is expensive is the computation. On on cloud clusters, GPU is expensive. Training algorithms takes time, takes compute, and that costs a lot of money. On my mobile, I can't train a model. It's too tiny. Like, these GPUs are not powerful enough to train big models. Okay. So storage is cheap, training cost is expensive. On small embedded systems, training a continual learning method itself is a challenge. Let's see for offline continual learning. It's very similar. Memory is very cheap. It costs 750 more times more cost to train models rather than to store datasets. It's very unclear why cost would be an assumption. It's just not reflective of reality. We should discard this assumption. Secondly, privacy. This is tricky. The key claim here is that due to GDPR, users can request data deletion, or due to privacy policies, storage can be permitted only for a fixed duration. Hence, we need to delete past data. But this concern is very valid. This is very true. But does limiting the memory samples, the thing people do in continual learning, address this concern? We argue that no. Simply limiting memory is not enough to preserve privacy. Why? Simply because deep networks memorize information. If you just delete the data, but retain the information in deep networks, it's not really preserving privacy by any reasonable standard. And here are some examples where people have shown that you can reconstruct data. There are many papers published by, say, Nicholas Carlini, who shows the same thing in like large language models, large generative image models. It's very clear that deep networks memorize information, and this doesn't really address privacy. This goes further. In our paper towards adversarial evaluations for inexact continual learning, we show that catastrophic forgetting is in fact a good baseline for data deletion. But this is in contrast to continual learning, which wants to preserve the past information. So it's antithetical to both delete past to both remove information of users and preserve the knowledge. Continual learning is fundamentally incompatible with the goal of data deletion. If you want to truly remove all information from a network, you can't retain the knowledge. This is explored quite extensively in machine learning literature, and we need to learn from that and say that, like, well, if you want to preserve privacy, continual learning is not possible, or it's a different problem and needs to be tackled separately. All right. So why is this ugly? It's because eliminating this tiny memory constraint results in very different results. Very simple algorithms like fine-tuning on all past data, which is you take whatever the latest model you have and keep fine-tuning it on past data. This performs really well. And this is essentially what industry does when they get more data. They just take the latest model, they fine-tune a bit on the concatenated data set. And the question here is how to sample the data set. And we show that, like, well, just class balance sampling does the trick. Okay. This is why eliminating this cost is essential. Now let's dive into this detail. So what have previous methods done? Here is a table of previous methods. They try to make deep networks robust to distribution shifts. You get some new data, some new class, some like new distribution. They train on some past data, some new data, and try to generalize the network across these two distributions or across these k distributions. They have taken three principal directions. One is distillation. What does distillation do? Is that it enforces that your new model output should be similar to old model output, and hopefully this can accelerate learning. Or they have good sampling strategies to like effectively sample from past data and retain most of the knowledge in less time. Or some continual learning works posit that it's just the last layer which has gone off the track, and if we align this last layer carefully, then we have solved the continual learning problem to a good extent. Okay. So these are the three principal directions. And what we do in our work, compute-based continual learning, what does matter, which is published this CVPR, is that we take this new constraint, which is we want to reduce computational costs, and then test all of these methods across the time incremental, data incremental, class incremental setups. And we get very clear result. Past methods do not improve performance when computational costs are equalized. What you should do is sample random subsets of data with class balance and train on it using all your compute budget. That performs the best. What essentially these methods did is increase the compute and hence got better performance. But if you normalize it, then the best way to use the computer is just always fine-tuning on past data sets. This result was very consistent across a lot of different systems conditions we tried. We tried varying the compute budget. We tried the number of times that we trained for, the sizes of the stream. We varied different sampling methods. We varied a lot of across data sets. This was very consistent that the random sampling baseline with class balance was always the best method to use. This is why. But let's move on to the second ugly constraint that we find, which is not measuring rapid adaptation. Until now, this was for offline continual learning. For online continual learning, we need time-sensitive model updates. First, we ask, does past literature measure this? We say past literature has typically tested on like class incremental CIFAR or class incremental mini imaginary datasets. It's very hard to measure rapid adaptation on those datasets. Because how do we measure rapid adaptation? First, let's go to that. We measure rapid adaptation by measuring the accuracy on the next arriving samples. Okay, it's hard to do this for the online CIFAR datasets, etc., because of the class incremental setup. The next samples by design are of the same class. So it's like very simple algorithms will work on this, and you're not really measuring rapid adaptation in these scenarios. So what is the fix? A fix is you have time incremental datasets where samples come by time steps, and you can measure online accuracy there. You take the next arriving time step to the server, and you measure the model's performance on this next sample or batch. Okay. However, we find in our ICCV paper, rapid adaptation and online continual learning, that this stream of samples that occurs naturally have correlated labels. And this creates issues. Let's see. Why are correlated labels important and what do they impact the algorithms? The first claim we make is that the blind classifier has great performance. What is a blind classifier? A blind classifier is a model that doesn't have access to the images. It just takes the last k labels and predicts the most likely label as the next class. Essentially, it says, well, the next incoming sample is going to be similar to the class of the last incoming samples. This has great performance, not only in the class incremental setup, where this will be the case by design, but in natural streams. And the performance is so competitive that it surpasses some online continual learning methods on these datasets. But the blind classifier is ambiguously a bad model. It doesn't even take the images to classify the next sample. And we see that we can exploit this. We can train a deep network to clearly overfit to the latest samples by designing this algorithm called overadapt. It's very simple and it's very clearly a wrong baseline. What we do is as follows. We freeze our network and overfit the linear layer on the latest incoming samples. What this does is, essentially, we want to preserve the features so we don't train the whole network, but we want to just overfit to the latest samples. And by doing this, we achieve, by doing this, we achieve incredibly high performance on the existing baselines. So we present an easy way to hack this online accuracy metric, and we show that why is this bad? This is bad because this favors methods which simply overfit to data. We do not want methods which simply overfit to data, but we want methods which do this rapid adaptation but preserve information from past knowledge and retrieve it when necessary to predict on the incoming samples. We need this dynamic learning ability, but this metric simply says like, well, overfit and you will perform really well. We need to not incentivize bad algorithms. Okay, so what's the solution to this? What we say is, instead of evaluating on the immediate next samples, we evaluate on near future samples. The question obviously is, well, how near in the future? How much do we delay the evaluation by? Our solution is a very simple solution. We again use a blind classifier to estimate the delay. How do we do this? We say that the delay is the optimal delay that we should pick is the minimum delay we can use where the blind classifier performance drops to 0. So we measure the performance of the blind classifier. We see, well, it's dropping to 0 after 64 samples. So we fix the evaluation to like, well, at every incoming time step, I will evaluate on the 64th next sample to data. This removes any spurious label correlations, and we can measure rapid adaptation quite well. Why do we say we need the immediate samples? Because if we take samples too far, it's not measuring this rapid adaptation thing. It's just measuring future accuracy, or what people typically call like, what is that thing called? Yeah, they just measure future accuracy. And this is not what we want to. We want to see whether it can rapidly adapt. Hence, we want to say immediate future samples which do not have label correlations. Take that one. And then we benchmark using our new metric, which is near future accuracy. And we see very surprising results. In the first string, a simple KNN simply freezing a network and using a KNN as a classifier performs really well. I'll come to this method in later slides. But when you have slightly more compute budget, then the best thing to do is to train offline. You should not consider the immediate incoming samples, but just train on past data and then predict the new samples. This is very surprising. This says that, well, you don't need to adapt as rapidly to the distributions on natural data streams. Is this good? This could mean that the natural data streams are just not requiring rapid adaptation in the first place. That could be a very real case. But this is what we see, and at least measuring online classification accuracy is clearly bad, and we should not do this. It's unclear whether near future accuracy is the thing to measure. Do we need data sets that actually have this rapid adaptation? We don't know. But this is at least the first step towards a better measurement of rapid adaptation. We clearly need more work here, but let's go ahead in this direction, is the claim that we are trying to set. Okay. So these are all the assumptions that we want to make. Essentially, have online versus offline continual learning. Online continual learning should measure rapid adaptation. Offline learning need not. Do your continual learning within a compute budget, and the task is it should match fine-tuning with fewer iterations. Then continual learning algorithms are useful. Don't impose any specific task constraints that like, I'm going to study class incremental learning. Use them as edge cases and don't make any distributional assumptions, and evaluate on different such streams so that you're robust across all of these edge cases. Don't use memory constraints, and if you're doing online continual learning, measure rapid adaptation carefully. Don't measure online accuracy without checking if you're just overfitting to the latest data. This is a summary of the past things. Now I come to a new way of doing continual learning. As I motivated before, Past algorithms try to make deep networks generalize across different distributions. They want to do that. When they do continual learning, their essential problem is compute efficient distributional generalization. And they did this by various approaches. We take a completely different direction. We say, don't try to make distributional robust networks. What you can do instead is augment your network with a continual data structure. What is a continual data structure? A data structure is this like external knowledge bank, which can have a dot add property and a dot retrieve property. Dot add property when I want to add new samples to the knowledge bank, and retrieve property when I want to see like, oh, I need to classify this thing. What past knowledge should I use to do this task? This will give us a very informed algorithm for doing this fast continual learning that we need to do. Okay. So what's a simple first cut solution that we propose for this continual like data structure that we want to do? We say, well, fix your DNN, just use a pre-trained deep network and do KNN on top of it. So when you get new samples, when these new samples are arriving, you just forward pass, you get features, you predict on the new on the incoming data, because that's the setting that we are doing, online continual learning. And once the label is revealed, you add this sample to your knowledge bank, which is you add it to the neighbor set of KNN. And you keep doing this. Now you can see this is blazingly fast because this requires no deep network training. You're essentially predicting, adding a sample to KNN, predicting, adding a sample to the KNN. And with approximate KNN methods, this is very fast. It operates in milliseconds over tens of millions of samples. Why is this? Why did we choose KNN? Why is KNN attractive? It's attractive because it gives us this interesting property of consistency. What I mean by this is that we can guarantee that we will not forget any past training data. If you give me a new sample which is seen before, I will exactly be able to give you the same sample back and predict correctly. Second is a natural insert operation. KNNs can insert data points to the KNN data structure, which in our case is this structure called hierarchical nearest small world. But it allows this natural insert operation. This is unlike deep networks where if you want to insert some information, you typically update your weight. So you overwrite some past weights, and this leads to forgetting. They're avoiding this issue entirely by just having this natural insert operation, which does not interfere with any further past knowledge. And this is very nice. This is what we want to do by KNN. This is the larger goal we want to do, which is a continual by design system. And this is the first cut solution that we propose. Well, how well does this perform? Because it's a big ask to not train a deep network. We see that it outperforms current state-of-the-art online continual learning algorithms by a very large margin. Like we are talking like 20 to 30% on like online benchmarks. And this is when we use very little compute. Every deep network updating algorithm we have given here does one gradient step every batch of samples it encounters. But we can do per sample prediction and much faster than any of these deep networks can. And similarly, here we show for online accuracy, but online accuracy is not a great metric. So we can see performance of this method here on the near future accuracy. And even on the near future accuracy, this performs really well, because this can do the thing where like it queries past data, sees what is important, and retrieves it to predict the next sample. It can do this knowledge accumulation for rapid adaptation in the fasting. All right. So it has shockingly good results. And we think that hence developing these continual data structures is a very interesting direction to pursue. We get large gains. This can be deployed immediately on any cloud system, can even be deployed on mobile, because unlike current methods which have to update deep networks, this need not update any deep network. We can do efficient inference on mobile with, say, mobile nets, and this just has to implement a KNN on top of it, which is very computationally cheap and very efficient. Okay, this is our work. So in conclusion, what we say in our recent work, Online Continual Learning Without the Storage Constraint, is that updating a deep network overrides information. And if we don't know what knowledge is stored where in deep network, which we have no idea, deep networks are a black box, harshly updating this causes forgetting. In like, we can replace this by having this separate continual data structure, which is not the deep network, where we can update this, we can accumulate knowledge, and we can predict using this knowledge. What we propose is a very simple data structure, which is KNN. We can do better than KNN, but I think this is a promising first step to take in this direction. So, lastly, to conclude my talk, I would want to give some example applications for the aligning research with practice that I mentioned before. These are toy applications that I explored for things where I think continual learning can be very useful. We take the case of active learning. Let's firstly just quickly describe what is active learning. The problem statement is you have to select a small training set among a set of given data to be labeled, and you have to minimize cost here. So you have to, there's labeling cost involved. You need to label as few samples as possible. What what active learning approaches typically focus on is this part, which is which sample to select. They develop better query functions. We are not interested in this. We will focus on a very different part, which is in this active learning process, when you train a model every time you want to collect new samples, the training the model is expensive. All active learning works typically just train this model from scratch, and we really don't need to do so. We think we can improve this by quite a lot. Well, how do we improve this? We can improve the training of this fitted model by training a much smaller substitute model. In our paper, Sampling Bias in Deep Active Classification, we showed that we can use a very tiny model. So instead of training big models like BERT, we can use this model called FastText, which runs on ImageNet scale datasets in less than 1 minute on a CPU. It gives you a fitted model back, and then you can use this model for selecting the samples. Once you've curated your small actively labeled dataset, then you can train a large model on it and get comparable accuracies to training a large model on this big dataset. Your cost overall, which is getting the active dataset and training a large model on this small dataset, is minimized by quite a large margin. This can do efficient active learning on large scale on text data. However, on images, we don't have models like FastText, which can run in less than 1 minute on CPU on large scale datasets like ImageNet. What do we do here? We have to use deep networks, but we can use smaller deep networks. There is a nice work called Selection by Proxy, which is published in ICLR 2020, which showed that this is effective, and you can use this to sample points, and you get very similar points as if you use very large networks. What we say in our work, CL Active, Episodic Memories for Rapid Active Learning, which is published in COLAS 2022, is that we don't need to retrain these small models from scratch, which everyone does. We can simply continually update these proxy models. This minimizes the training cost by quite a lot, because, well, when you continually update a model, you use far fewer iterations, and you can achieve very similar performance. We get very large reductions in training cost to the base active learning, which is training from scratch. We get up to 89%, 89 times reduction on CIFAR datasets, 7 times on ImageNet, and 61 times on Amazon Review. So this works with text classification as well. We can do it on
Can I
fast
ask a
text.
question?
Yes.
Yeah, when
Uh,
you say that you are training a smaller model, so obviously it will take lesser memory to train and lesser time to train, given that all the size of the model is small. Then
yes.
the cost of reduction which you are claiming, is it this
Yes.
cost reduction comparison to the larger model, or is it
Compared to the
because
larger model,
smaller
yes.
model will Yeah. So we
Yeah.
shouldn't we be comparing between like smaller models itself?
Yes, we can compare like how much do we improve by continual learning, and that we mentioned those numbers in the paper as well. But this is the overall to just to motivate why continual learning can be useful here.
I
This is
understand. Like given that in the normal this active learning setup, there would be a larger model which needs to be retrained again and again. What you are proposing is we can use continual learning instead of that.
yes on a smaller model.
Or use instead of using a larger model, instead of using a larger model, you are using a smaller model. But smaller model will
Yes.
give a reduced accuracy also,
Yes, but we
isn't
don't
it?
care about accuracy on the small models. We only care about what samples they select,
Okay.
and we
Yeah.
can and we can show that they select the same samples.
If you continuously keep getting better samples and use
Yes,
smaller model, then you would like to train a larger model in the end by
yes,
after
exactly.
certain blocks. Okay.
Yes, exactly. This
So you are
is
using a
the
smaller
sort
model
of
for sampling instead of using it in production.
yes, yes. But the goal of active learning is to select the samples, is to curate this small label data set. And if we
Yes,
do
yes.
this, we get very large reductions in cost. And like this is a very practical like it's a toy application. Like people don't really do continual active learning these days with these large what do
No,
you call
so
it?
this
These
has
overhead
very
models.
nice application given that suppose you have lot of video data, and if you just
Yes,
want to select some of the interesting sample images from that, you can use a smaller model in that case. Okay.
exactly. Like this is I think this is a very nice application to show like where continual learning can be used effectively in practice. Uh, and this is it. Now questions. I will just go to the chat questions first. The first question, oh, Kunal, is can you repeat the point about Canaan?
Yeah, yeah, yeah,
Whoops,
yeah.
I will repeat this. So, was the question why Canaan or like how? What is this ACM system? What does it do?
Yeah. Why Canon basically?
Okay, so why Canaan is because Canaan has this very nice properties. Like it has the consistency property, which is it will never forget past data. Which is if you think about it, it doesn't exist on a lot of current methods. Any parametric method will typically not give you this guarantee, and this guarantee is very useful for continual learning. Secondly, you can just insert new data points. Continual learning essentially has been like how to insert data points into a deep network, but that has been hard because we don't know what is stored where. You overwrite stuff when you do this. But Canon is a very simple, you can simple, it's very easy to see why you don't overwrite anything and how you continually accumulate knowledge by simply
But
continually accumulating these
you have to
results.
keep the data features also in that case, right? Like in the
Yes,
memory,
yes.
because
It is RAM
with the
intense.
DNN, that is the feasible point. That suppose you have ImageNet scale data, you would not require to keep all the data features in that case. You can just
Yes,
keep a trained model.
yes. That is why selecting the correct assumptions is paramount. The issue is like, do we really have that much constraints on RAM? So for doing the experiments in clock, which was like 39 times the size of ImageNet, we required around 100 GB of RAM. Servers have like a terabyte of RAM. Like this can scale up to a billion data points. There are papers which have shown cannons on like on production systems in on billions of data points. This is doable. There are out of RAM Canon approaches. Solving the memory with Canon is very easy. But deep networks are very hard to train. If our assumption is that we want to minimize compute, storage is cheap. We can store all features on hard disk. We can load the features in RAM is a more tricky assumption to make, but it's possible and it's very easy to do out of like RAM Canon methods as well. If
There
we
is
get
one
with
more
these
assumption
assumptions,
here, right? There is one more
hmm?
assumption here that whatever distance metric that you are choosing for applying KNN,
Yes,
that is actually the correct distance metric for these kind of features. The point with deep learning models is
yes,
you give in an input and you take out an output, and in the higher dimensional space, how this distance metric is being done, we are not concerned directly. Here we are saying that we given that n feature length feature, and two features we are using, suppose Manhattan distance, or we are using cosine similarity, something
Yes.
like that. So we are saying that the constraint over this space is this cosine space distance basically.
Yes. Yes. This is an important constraint that this imposes. If it's not good at cosine similar, if the space is not good at cosine similarity, you won't get very good results. But then
Correct.
that
I mean,
is
then you have
something
to
happening.
design the model in such a way that the features that you learn are learned in that cosine similarity metric space eventually. That if you are not explicitly putting that constraint over the model, more features can be learned arbitrarily. Yeah.
Repeat it again.
I was just saying that you would have to put that kind of a constraint over the model training itself. Suppose
Yes,
when you
typically.
see these clip like models, they are trained with certain loss functions which help in formulating the constraint that
Yes,
that they learn
yes,
cosine similarity space. Yeah.
yes. Nearly all deep networks we saw and evaluated worked well with cosine similarity. So we just use cosine similarity as a metric. It just happens so that like the pre-trained models that typically are available just perform well with cosine similarity. So we can just fix it and this works. But this need not be the
Which is an
case.
important assumption also. Yeah.
Yes,
Okay.
which is an important assumption to make. Yes, this is an important shortcoming.
Right, that's true about the cosine similarity, though. Even in test time adaptation methods, whenever you're trying to design an adaptation, cosine similarity happens to be really good in the feature space. One question that I have, are you done, Kunal? Can I ask mine?
Yeah, I'm good.
Okay. Do we process this batch-wise, or is it working even for per sample basis?
This is sample wise. This
Okay.
is so fast it can process data one sample at a time. So what this allows is the reason the accuracy improvement is this high is that the adaptation works very well on sample level, and the information retention is very high. Information retention essentially is if at the end I train on a test set of all past data, do I perform well? And it shows that the consistency property not only preserves train sample seen, but also generalizes well to unseen test samples. You can predict test samples very consistently across a very long span of time. But if you see on clock, existing methods just fall off very quickly on very like they don't perform well on past samples at all. Whereas we have like a more like uniform line. We preserve more past data.
Yep, this makes more sense. Very interesting talk. I mean, this was very knowledge loaded session, a lot of information that I didn't knew could be analyzed about continual learning these days. I mean, as far as I have seen bigger industries working, they just prefer to fine tune or retrain their existing model with whatever label data they can procure over time. And they're not really very keen on adapting towards continual learning because
Yes.
it still stays like more like a fantasy realm. Okay, this is possible, but do we need it? We don't want to know.
Uh, like in my CV paper, I say this is not the case. Like if you take the
Mm,
assumptions that they're assuming, like well, they can store all samples, like that's not an issue, and
yep.
like they have compute constraints. They want to train their model fast and with less GPUs. Then the
Mhm,
best thing to do, in fact, is to do this fine tuning on past data with random
mhm,
subset sampling.
mhm. Also, the point you made there with the fact that if you want to focus on data deletion, you cannot continue learning. So they are very opposite and at crossroads kind of situation. This is very
Yes,
interesting and very strong as well.
yes.
Right. So I
To be
think
clear,
those.
our work is not the first work in machine learning. This has been claimed by a lot of works before. What we
Uh-huh,
introduce is like catastrophic forgetting explicitly as a baseline. But
right. Okay.
like there's a lot of cool machine learning works which will go very deep into this. Why is this the case? Like what how should you preserve privacy, etc., etc.
Mhm. Okay. So this is more around privacy preserving part.
Yes, this is how
Okay.
how to forget information. You like you re, your objective is to forget information, just like
Okay.
how to do that.
Okay. Nice. So these were my questions, and I don't see any in the chat. And for more, as you suggested, I'll put your email address in the description and in my LinkedIn post where I'll be sharing the talk. Thank you so much, Ameya.
Yes.
That was.
Uh,
Are you close
I'll
to
just
finishing
add
your
one
PhD?
thing.
Yeah.
Like, yes, the things that we propose are like not anywhere close to the last things. Like, this is just the first steps in each direction.
Mm-hmm.
We can perform very well in this setting probably if we just make the right assumptions and then go with it. Similarly, KNN is just it's a very silly method. Like, this
Mm-hmm.
is nowhere close to the best method. We can develop better continual data structures, and I'd be very excited to see work in this
Mm-hmm.
direction. Yes, this is all.
Yep. Okay. So are you close to finishing your PhD?
Yeah. Yes, I am close to finishing my PhD. I
Yep.
have a few more months left.
Yeah. I see all the work presented together, so it made sense.
Yes.
Great. So I hope when this talk goes out,
I
people
have a quick
get
question.
inspired.
I have a
Yeah.
quick PhD kind of question.
Yeah.
Um, so how do you track your progress during PhD? Do you keep a tracker or something?
Uh, so I just proceed on, like, sometimes I find interesting results, sometimes I don't find interesting results. There is no
Mm-hmm.
like, what I want to publish is like something which people can see and say, oh, this is cool. This leads to problems. Like, my method
Right.
is not the best method. Between GDOM and the computational budgeted paper, there was like 1.5 years where I had no publications.
I see. I see.
I
Mm-hmm.
was just exploring applications of continual learning, and
Do
I
you
came.
suggest, is there a principled way of keeping track of how the progress is being done between you and your professor, for example?
Yes, we have weekly meetings, and like
Mm-hmm.
my professor asks me for like, oh, what are the updates, etc. That
Okay.
happens. But
Okay.
a key thing that I do differently in my research is that I start with a complicated method, and then I start removing things into it
I see.
until I
I
have
see.
the basic thing left. I didn't
I
want to
see.
design ECM. This was not even the goal. We found this paper
Mhm.
called contextual memory trees, which is
Okay.
beautiful. It's a very nice algorithm for continual learning, and we wanted to introduce that with deep networks. We introduced that, and we that was the original method that we proposed. This has been getting rejected since last knowledge, but that got rejected. Like, that didn't work. That
Okay.
worked well, but like we removed a lot of components. We removed the trees, we removed the dreaming updates, and still performed well enough. And like, we ended up with just a KNN, and we're like, well, this
Okay.
is essentially where the performance is coming from. I
Okay.
think this trick of like keep removing components until you are left with a base thing, which is the core reason for improvement. That is really cool, because then the method is very simple. People can use it, and it's really like, it's more clear to see why things are happening the way they're happening.
I wish I could just take this clip of your answer and put it out for more people to
Uh,
understand because, yeah.
there is in fact a talk by Professor Kilian Wienberger on this, which I really like.
Mhm.
I can just send you the link for the talk.
Yeah, please do. Please do send it to me on the email. I mean, this is
Like,
one thing that I really want to emphasize on as well because I was trying to explore continual test time adaptation, and I see people getting towards more complicated structures like 7, 8 components working together, giving you one result. For example, I was exploring a paper quota. And I was trying to do the same thing that you suggested. I was trying to remove the stochastic restore component, the augmentation component, and see which one was affecting the results the most. And yeah, it just kind of I have been just like you suggested about you mentioned your break 1.5 year. I've been down 1 year in my PhD, and I was trying to work on an approach where I'm not using anything fancy. But the pressure builds up, and then you're at some point just wondering maybe I should get 7, 8 fancy components together and produce something that's state of the art. And that pressure
yes.
is real. So yeah, your
Yes, the
answer
pressure
was.
is real. Like, I can see like other PhDs publishing like 2, 3 papers consistently every year.
Mhm.
It
That's
it kind of
no, but
sucks, but I think this is the correct thing to do. I think
yeah,
like
no, the
I don't
your
want
work.
to flood
Mm.
conferences with random papers.
That's true. No, your work speaks volumes. I hope when I'm publishing next, I get to meet you in a conference. It was a very great talk. It was very well summarized and very well assessed.
Uh, Also, small note, on continual test time adaptation, there's this really cool work called ARDM.
Mhm.
Essentially, what it says is this: when you do test time adaptation continually, you can, like, the previous sort of time steps, like the previous sort of distribution you're adapting to, is not useful for the current time step. So you can just reset the model every time,
Mhm.
and like you get equal performance. So essentially, you're not leveraging any of the continual learning parts.
Mhm.
I quite like the paper.
What's the paper called?
It's called Ardum, a simple approach that, so it's very similar to the GDM title, but like but with the continual test time adaptation. It's by
Okay.
Matthias Bedke's group, I think. I can send
Okay.
you the link for the paper.
Okay. Yeah. I think most of the paper come from that group, so makes sense. Okay, I'll find it and I'll reach out to you on email for more information about different things. But yeah, it was truly a pleasure hosting you. Thank you so much for getting time for the talk. It was
Thank you
great. It
for
was
hosting me. This
great.
is amazing.
Thank you. No, and also I'm very apologetic for the last minute hassle that you had to go through. I'm so
Oh, that's fine.
sorry. Okay,
Zoom,
great.
Zoom issues. I've been through the COVID era.
Right. Thank you so much. Thank you for people who could join even after we started late. I'll be sending out the link in the mailing list soon. Thank you so much.
Thank you.
Have a good day.
Bye bye.
Bye bye.